All right. I will begin with the word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for your many blessings to us, Lord. In your name I pray. Amen. All right, so I just wanted to go ahead and walk through some proofs we didn't quite get to last time. So I was telling you guys that the work of Lamé or Lame or Lam, or anyway, I'm saying it wrong, wasn't quite right because he assumed that the sort of abstract numbers, algebraic integers of a particular type, had a unique factorization domain property, when in fact they did not. This was known to Kummer, and ultimately Dedekind was able to formalize and fill in the gaps of his arguments and put what are called ideal numbers on a firm logical grounding. Ultimately, there ends up being a theorem that says, yeah, well, there's an ambiguity of these algebraic integers in terms of the fact that they're not a unique factorization domain, but when you instead work with ideals, then at the level of ideals, there is a unique factorization property. However, that's great, but in the end, it wasn't possible to repair his argument and get a proof of Fermat's last theorem. I mean, a lot of it, I guess, was proved with the technology, let's say, that was developed by Dedekind, but not all of it. It stood on completely, not entirely unsolved, not entirely solved until recently. Anyway, this is the definition of a unique factorization domain. Every element in the unique factorization domain can be written as a product of irreducible elements. The factorization of any given element into reducibles is unique up to reordering and associates. So if I have x is equal to x1, x2, xn, where these are irreducibles, and if I have x is equal to y1, y2, that shouldn't be, I mean, it is true that it can be the same n, but, well, fine. Yeah, that should be matching. So same number. Then these have to be basically the same elements, just they could be multiplied by a unit. So in other words, the x's and the y's are associates. All right. Anyway, that brings us to what's called the ascending chain condition in a PID. This way of thinking was pioneered by Emmy Noether, who really brought abstract algebra to another level in the early 20th century. She was, I think, she was in Germany at the elite school in Germany, Göttingen, back before Hitler ruined all that. And then Noether was actually was at Bryn Mawr College for a brief period of time. Unfortunately, she died early, which is unfortunate because she was really fantastic mathematician. Much of the modern ring theory, which we know, is ultimately born from her and her students. Anyway, here we go. The ascending chain condition in the PID. In a principal ideal domain, any strictly increasing chain of ideals, I1, subset of I2, subset, must be finite in length. So if you have this chain of ideals, one nested inside the other and so forth, and on and on and on, it has to be finite in length. All right, so if we let I1 and I2, be a chain of strictly increasing ideals in a principal ideal domain D, then what you can do is you can form the union of all of these ideals. All right? And the union of all of those ideals will form an ideal, this union ideal. It's easy enough to see that if you take the difference of things in here, it's again a difference of things in there. And you can prove Uber closure using, it's going to be a little bit of set theory, it's an arbitrary union. But in any event, this is an ideal. The union of all these ideals is an ideal. And since we're in a principal ideal domain, that means there has to exist some D which generates this ideal. So D is in the ideal. That implies that D is in, since the ideal is formed by a union of ideals, if it's in the union, it must be in one of them, right? So D has to be an IN for some n, but check it out. Everything in the ideal is a subset of the union ideal, but the union ideal is generated by D, and that is a subset of the In, because In, again, was containing D, and of course, if you contain D, you contain the principal ideal generated by D. And so there you have it. Everything in the chain is a subset of In, which says, in other words, that this chain must be finite in length. This chain has to terminate at finite order. And this is the ascending chain condition. An ascending chain of ideals in a principal ideal domain has to terminate. Yes? A question? Yay, questions?
No, just lost.
Oh.
Also, remember what time this thing starts.
Oh, that's okay. We start, 4:45 ideally. I'm just going to wrap this lecture up, then I'll take other questions. It won't be long. Because I wanted to really start tomorrow in the next chapter, and not, because we keep doing this thing where we're straddling one chapter and the next, and I just want to be in the next chapter at the start of next lecture, so I'm just getting the rest of it out of here. And it's unfortunate, because, I wish everybody was paying attention to this, because it's really, really beautiful. But here it is. Now, unique factorization of, then the question is, well, what is a unique factorization domain? Like, what are examples of unique factorization domains? By the way, it's not at all obvious, this principle, this ascending chain condition I just showed you. What on earth does that have to do with unique factorization? That's not at all obvious yet, all right? So first of all, I'm just reminding you, what examples do we know? Well, we know that the polynomials with integer coefficients are a unique factorization domain. The gory detail of that is in page 305 to 304 to 305 of Galilean. That wouldn't have been any help. That wouldn't have been covered by the theorem we're about to look at here. But if f is a field, that gets us that f of x is a principal ideal domain. By the theorem 3.4.17, there we proved that if you have a field, polynomials over a field form a principal ideal domain. The proof of this theorem, I think, is really one of the most interesting, and it's really one of the most interesting theorems that we'll look at here. So here it is. Every principal ideal domain is a unique factorization domain. There are 3 stages to this proof. We pick a non-zero element of D, where D is a principal ideal domain. I gave the name to the set of units U, but I didn't stick with it. Like, I don't know, I thought I was keep saying things are in U, and so I wanted to create a name for it, but turns out this was wholly unnecessary. I could delete it, but anyway, I'm telling you this because it's very fascinating. I don't know why I'm telling you this, I'm sorry. Anyway, so non-zero element, a non-zero non-unit element, all right? So the game plan is as follows. Number 1 will show that every factorization of A naught contains at least one irreducible. Number 2, we're going to show that there is a factorization of A naught into a product of irreducibles. Once you know one, you get many. And then finally, we'll show uniqueness up to associates. So step number 1, if A naught's irreducible, then we have shown A naught contains an irreducible. Well, that was not hard. Otherwise, A naught is equal to A1 times B1, where A1 is not a unit and B1 is not 0. All right, so if A1 is irreducible, well, we're done. We just showed this is supposed to be A naught, typo, sorry. A naught contains an irreducible. Otherwise, suppose that A1 is equal to A2 B2, where B2 is not 0 and A2 is not a unit. All right, then we just keep doing this, and we define A plus n, an plus 1, and an plus 1 not a unit, and bn plus 1 not equal to 0, for which a sub n is equal to a sub n plus 1 times b sub n plus 1 for 3, 4, 5, so on and so forth forever and ever. So if you look at this equation, what's that say? It says that the ideal generated by an is going to be a sub-ideal of the, it says that this ideal is a subset of that ideal, right? Because an is automatically a multiple of an plus 1, right? So we get this inclusion. And we also know that they're not equal because of the condition, the condition that fell out. Anyway, so we have a strictly increasing chain of ideals. So by the ascending chain condition, there has to exist a K for which this chain of ascending ideals terminates. And what does it take for the chain to terminate? It takes one of the A sub Ks to be irreducible. So we have proved that any A sub naught in a principal ideal domain contains an irreducible. So there's at least one. There's stage 1 of the proof is done. Stage 2, if A naught is irreducible, then we have a factoring of A naught into irreducibles. This is just kind of dumb, but okay, if it's 1, it's done. Otherwise, by 1, there exists P1 and a non-unit C1 for which A naught is equal to P1 C1, right? It contains an irreducible, and there's something else left over. Now, if C1 is an irreducible, then we're done, because we've got a product of irreducibles as A naught. But otherwise, C1 still contains an irreducible because of 1. So that gives us C1 is P2 C2, where P2 is irreducible and C2 is not a unit. And then we get another ascending chain of ideals. A naught is the ideal generated by A naught is a sub-ideal of the ideal generated by P1, which nests inside the ideal generated by P2, and so forth. Okay? So we get an ascending chain of ideals, which again by the ascending chain condition has to terminate. Where does it terminate? It terminates at, let's say, P sub t, and that has to be an irreducible to stop the chain, the creation of further links in the chain. And consequently, A naught is a product of P1, P2, pt. In other words, it's a product of irreducibles. So in a principal ideal domain, we can take any element and we can factor it into a product of irreducibles. Now, this still leaves us uniqueness, right? Because the unique factorization domain property has, first of all, the existence of irreducibles to which we can factor, but also the uniqueness of said irreducibles up to reordering and association. Well, association is probably the wrong thing to say, but associate. I don't know what to say. Associates. So here it goes. So suppose you have two factorizations, all right? First of all, this is going to be proved by induction on T, the number of irreducibles in the left factorization. If T equals 1, then you have A naught is equal to P1 is equal to this product of these S irreducibles over here. Okay, so unless S is equal to 1, then we have if S is not equal to 1, we have a reduction of P1, which contradicts the irreducibility of P1. Consequently, S has to be equal to 1 as well, and we just get A naught is equal to P1 is equal to Q1. So guess what? They're unique, right? So actually, if you just have one irreducible, there's not even, they have to match up. There's not even room for an associate. So then we're going to suppose inductively that any factorization into less than T irreducible is unique up to associates. So again, we'll look at A naught is equal to that, right? Notice that P1, of course, divides these guys. All right, by this equation, we can see that P1 divides Q1 times Q2 Qs. Hence, by an exercise that I actually did not assign, there exists some Qj which P1 has to divide. It's basically the extended Euclid algorithm for products of irreducibles. And so anyway, we have to have P1 is equal to Uj Qj for some j. And so you can put that in there. Here's Qj Uj for P1 instead of P1, and then you got P2 pt. On the other side, you got Qj Q2 Qs. I just moved the j out front for the sake of emphasis.
Yeah. So I suppose if you're going to do that, you should put Q1 in that.
Well, j might be 1. I don't know.
Yeah.
You're right. 1 is in there somewhere. Yeah, you're probably right. I should put 1 there.
Just for clarity.
Yeah.
To make sure that people aren't like, oh, so j is 1.
Yeah, you're right. I probably should put a 1 there. I can afford that. I'll try to do that later. Thanks. So then by cancellation property, we've got Uj P2 pt is equal to Q1 Q2 Qs. What's that?
Which means not good things are happening.
Which right. So then, well, but that's great because then we have a product of two irreducibles of less than R things. There's R minus 1 factors now. Then by induction, we know that these are unique up to ordering and associates. In fact, if you've been taking number theory anytime recently, you might recognize this as it's really just the prime factorization argument. I mean, like the fact that any integer can be written as a product of prime factors. Like the argument for that is very similar to this in some regard. But anyway, there it is. So any principal ideal domain, because it satisfies the ascending chain condition, we can argue that there's unique factorization of any element into irreducibles up to factorization. Consequently, if f is a field, then f of the polynomials over the field is a unique factorization domain. That's pretty low-hanging fruit because we already proved that in this theorem we proved that if f is a field, then this is a principal ideal domain. Polynomials over a field are principal ideal domain. Consequently, they're a unique factorization domain. Theorem 3.7.10, every Euclidean domain is a principal ideal domain. And I'm not too sad to not be doing this in the like prime time class time, because this argument is so familiar. I'll run through it with you. But look at this argument. So if D is a Euclidean domain, what would we do? It has a norm n, right? If I is a non-zero ideal in D, what do? You construct a set S, which is formed by the norms of elements of I. But this is a non-empty subset of non-negative integers. Consequently, you can use well-ordering principle, pick a smallest member, S naught. Corresponding to S naught, there has to be an element I called X naught, such that n of X naught is equal to S naught. You apply the division algorithm to an arbitrary thing in the ideal. That gives you a quotient and a remainder. But the remainder also has to be in the ideal because it's the difference of something in the ideal, and by uber closure, the multiple of something in the ideal. Consequently, it's in the ideal, but it can't be in the ideal unless it's 0, because otherwise it would contradict X naught being the element, X naught producing the smallest degree. Consequently, the remainder is 0, which means that we just have that, if the remainder is 0, that means that Z minus QX naught is in the ideal. In other words, Z is equal to, excuse me, yes, actually, R is equal to 0, so Z is equal to QX naught. That says that Z is an element of the ideal generated by X naught, right? So, but that's an arbitrary element in the ideal. So that shows that the ideal is found in here, right? So the ideal is contained in this, but the smallest ideal, which contains X naught, is the principal ideal generated by X naught. Consequently, I is equal to X. I is equal to the principal ideal generated by X naught. Also, if I is equal to 0, well, 0 is principal also, because 0 is generated by 0, so it's principal ideal. So there you go. Every Euclidean domain is a principal ideal domain. This, you might recognize, is exactly the argument we gave for theorem 3.4.17, which was the one I was just talking about a second ago, that the polynomials over a field form a principal ideal domain. There, instead of using norm, we use degree, but of course we know that the degree is the norm on that. So, and then finally, every Euclidean domain is a unique factorization domain. So here, we just proved Euclidean implies PID, but we already proved that PID implies UFD. So we get that Euclidean domain implies PID implies unique factorization domain. And so that's the way of the world. You should be able to give like counterexamples. So this implication, Euclidean domain implies principal ideal domain implies unique factorization domain. This chain of implications only goes one way. There are counterexamples to the converses of all those implications. So principal among these examples is that the polynomials with integer coefficients is a unique factorization domain, but it's not a principal ideal domain. We found we produced an ideal in the ZX, which is not principal before. Like, you look at the ideal generated by 2 and X, polynomials with even constant coefficients, that's an ideal, but it's not principal. So the polynomials over the integers is not a principal ideal domain, and yet it's a UFD. So UFD does not imply PID. However, the converse is true. PID implies UFD. We just proved that. And then the example of a PID, which is not a Euclidean domain, is just ugly. Okay, so I give you a link if you're interested, but that's not something I'm going to expect you to reproduce. Or, I mean, honestly, this is a little bit above our level at the moment, okay? To be totally honest. And that's why Galilean doesn't attempt it in the book either. He just gives a reference to an author from the late 40s, I think. Finally, theorem. If D is a unique factorization domain, then the polynomials over D forms a unique factorization domain. The fact that the integers polynomials over the integers as a UFD is a subcase of this theorem. I'll give exactly as much proof as Galilean on this one. All right. Finally, the proof of the Eisenstein criteria, as promised. So, so Galilean credits Richard Singer for this proof. You take a polynomial, f of x, a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, plus da-da-da, plus a naught, a polynomial with integer coefficients. We assume the criteria of Eisenstein. In particular, we assume that p divides what? All of the non-leading, like all of the coefficients for what? All of the... everyone but the first one. It divides the last one is fine. But the thing is with the last one, p has to divide it, in fact. But p squared does not divide it. Yeah, so we have to have p divides everything except for the leading coefficient, and p squared does not divide the constant coefficient. This is Eisenstein's criteria. So towards all the proofs of this that I've seen are contradiction proofs. I'm actually kind of interested, is there a constructive proof? But I haven't bothered to ask anybody who would know yet. So suppose f of x is reducible over q towards a contradiction. We had a theorem that says reducible over q implies reducible over z. So suppose that you have f of x is equal to g of x, h of x, and z. Polynomials are with z coefficients. Modulo p, this f of x reduces, remember, so all of these things are 0 mod p, right? So the polynomial an x to the n plus stuff that's 0 mod p reduces to an x to the n. It's pretty awesome. So an x to the n is equal to the product of the reduced factors as well by the homomorphism, the reduction homomorphism. I should have assigned that as a homework. Is there still time? Anyway, but x is an irreducible in ZPX, right? And ZPX is a unique factorization domain because ZP is a field, right? So that if you have, this is an, right, and then like x times x times x times x times x times x. So it must be that x divides this and x divides that. Must be that x is a divisor of both. If it was a divisor of just one of them, that would mean that the other one, there's a small gap in the argument there, but there's a reason that x has to divide both of them. Anyway, from which we deduce that, so if x divides this and x divides that, the reduced polynomials, that means that when you plug in 0, you get 0, right? If x is a factor by the factor 0 theorem, correspondence theorem, we know that 0 gives you 0 and 0 gives you 0 for h and for g reduced. But what's that mean? That means that p divides g of 0. And that means that p divides h of 0 in the original, polynomials over z. Consequently, if you look at f of x equals h of x g of x, where f of 0 is a sub naught, which is also h of 0 times g of 0, this divided by p, this is divided by p, so that's divided by p squared. Oopsie, contradiction. Consequently, no reduction is possible. This is like way easier to understand than the contradiction proof that's given earlier in Galilean, I think. And then here, I just go into the example that I gave you guys in class, which is that in z adjoint square root of minus 5, you can, first of all, the only units in this are plus or minus 1. In contrast to the Gaussian integers, which have units of plus or minus I and plus or minus 1. This only has plus or minus 1 to work with. So it's really easy to see what's associates and what's not associates. If it's not equal or minus the other thing, it's not an associate. So when you look at this factorization, 2 times 23 and 1 plus 3 root 5, 1 minus 3 root 5, it's clear that this and that are not associates. Furthermore, this argument, all of this stuff down here is just to prove that these are irreducibles. So we have a factorization of 46 into this pair of irreducibles and that pair of irreducibles. They're not associates. This is clear evidence that z adjoint square root of minus 5 is not a unique factorization domain. So, on this next test, there might be questions like, give an example of something that is not a unique factorization domain. And this is pretty much like a go-to example for that. In contrast, z adjoining the square root of minus 1 is a unique factorization domain, like the Gaussian integers, is because it's a Euclidean domain. And Euclidean implies principal, and principal implies UFD. That's what we proved today. Hey. All right, well, now we have made it to the end of lecture 29. So I will put this away and answer your questions.
I'm not smart enough to ask it.
That's fine. I'm not smart enough to answer them either. So. I mean, I can start putting problems out of the book and trying to solve them if you want me to.
Did you go over the solutions to the homework we just turned in?
No, I only have what I showed you guys last time. I haven't had a chance to work out more yet. So maybe next time.
All right.
I have hope.
Because, for number 39 in section chapter 6.
I mean, if you want to ask me about one you just turned in, want me to try to work it out here, I can try. Which one is it?
It gives an answer in the back, but I decided not to copy it down.
Oh, are you talking about the x to the fourth plus 1?
Probably.
Number, which one are we talking about? It's
Number,
chapter 17?
oh, maybe. Yeah.
So, number 29.
29.
Yeah, I shouldn't attempt this right now until I should think about this some because it seems like this one's somewhat beastly
Yeah, okay.
from what it has been rumored to me.
Because I really could copy that down, but I wasn't gonna. I didn't understand a word of it. So,
It might be a hint too, you know?
yeah. All right.
I mean, I could take a swing at it, but
Okay. Later is good.
I mean, I will tell you this much. X to the fourth plus 1
Yeah.
is an interesting thing. So if you look at f of x equals to x to the fourth plus 1, right?
Okay.
It's pretty easy to see that f of I is a solution, right? Is that right? Maybe that's not right. No, it's not even true. That's 2.
Yeah.
But, you know, if you had the fourth root of I,
Okay.
that'd be good to go, right?
Yeah.
So the question is, what is the fourth root of I? So let me share with you a little bit of complex analysis. The fourth root of I is equal to, so what you got to do is you say it's really it's easier to understand when you put it in the fourth root of, what is I? Well, I is e to the I pi over 2. So like e to the I, how's it go? I pi over 8. I think that works. E to the I pi over 8, I believe, is the fourth root of I. We can check it. What happens if you raise that to the fourth power?
I.
E to the what? E to the I. Oh. Oh, I'm sorry. I'm an idiot. I'm trying to solve the equation x to the fourth equal to minus 1, right?
Yeah.
So it's not. I'm sorry. My mind is not where it's supposed to be. I was in the middle of a later part of the solution. I don't know what I'm doing. I'm sorry.
Okay.
I can't even explain why I wrote what I wrote. It's just really out there. X to the fourth equals to minus 1 is what we want. So all we want is a fourth root. One of the solutions, of course, is the principal fourth root of minus 1. This is the fourth root of, the principal fourth root of minus 1 is e to the I pi, right? So that is e to the I pi over 4. This is the definition of the principal nth root. To find the principal nth root of like the nth root of z, it's equal to the modulus of z to the 1 over n. That's the real 1 over n power. And then you do the exponential of I times the arg of z divided by n. That's the definition of the principal nth root. That will produce a solution of the equation if you call this thing w. Right? This solves w to the n equal to z. All right? That's not a unique solution, but it's a solution. So e to the I pi over 4 is a solution to this problem. I mean, in other words, this is a specific form, right? This is cosine pi over 4 plus I sine pi over 4. Also known as square root of 2 plus I times the square root of 2 over 2. And then the cool thing is, once you know one solution to one of these problems, you can generate the rest by multiplying by the primitive, whatever it's called, the root of unity, the generator of the roots of unity. So in this case, it's I. So basically, your solutions are e to the I pi over 4, I e to the I pi over 4, I squared e to the I pi over 4, and I cubed e to the I pi over 4. These are zeros of f of x, and then by the factor theorem, we actually can factor f of x equals x to the 4th plus 1 in the following way. I'm grouping them so that they're in conjugate factors. You know they have to be paired in conjugate factors. It's a real polynomial. So if it factors, it must factor. I mean, any real polynomial will factor into linears repeated and quadratic irreducible powered up. There's no like irreducible quartic of real polynomials, right? They all break down. It's just not pretty. And so this is like, x. Is there a way to write this prettier? I don't know. I guess I could write that as 1 over the square root of 2 times 1 plus I. I don't know if that's helpful or not. But minus 1 over root 2, 1 plus I, x plus 1 over root 2, 1 plus I. And over here you've got x. And so if I multiply that by I, that gives me what? Minus 1 over root 2. I minus 1, x minus, plus 1 over root 2, I minus 1, I guess, yeah. Multiply this stuff out, what do you get? You get x squared. You get minus this plus that. What happens is the i's cancel, right? But there's something left over from it, though. Oh, is anything left over, actually? I get 1 over root 2 times x minus, and then plus 1 over root 2 times x. I guess those are also canceling. I think the cross terms cancel, right? We're just left with what? Well, am I right about that? I don't know if I'm right about that. Let me just talk you into it. Anyway, you can multiply this out and you get 2 irreducible quadratics, which multiply together to give you x to the 4th plus 1.
Okay.
Yeah. In fact, if you just find one of these, you could use long division to find the other one. I don't know if that's great or not, but polynomial factoring in general is a tough business, I'm not, I know, I believe there's a cross term in here is what's bothering me. Oh, well, let's go on to other things. You guys got another question? Maybe. Did you guys already turn in number 10 here? Page 308.
Yep.
We could talk about that one. We could try. Does this look at all? I haven't looked at the back of the book yet. Is this it all related to what he does in the back of the book?
Not really.
Okay.
He has x squared minus a. He just gives a, I think, probably in place of unity of I don't know.
Now I'm intrigued. I can't wait to look at that problem. I assigned it mostly because it has an interesting and prominent place in the discussions chapter, and I felt like it's something we should try to work out to better understand what Galen's talking about. I'm not aware how much trouble it is.
The gives of what he does doesn't seem to relate to anything he said in the past. Is the main problem. Like,
Yeah, I guess I did look at it. This one you just use.
suppose a long chain of, if it's like this, then it's like that. So
You just
it
use
makes
Eisenstein for this, right?
I don't know.
Yeah, for these ones we just use Eisenstein.
These are all Eisenstein?
These are pretty,
Yeah, all but like one of them fell out really easily.
So we use p equals to 3,
Yep.
and note that 9 does not divide 6,
Yep.
therefore irreducible by Eisenstein.
Yeah.
Just, it's,
Yeah.
yeah, and then there's 29. Did I, mm-hmm.
How do you,
Ah,
I found a common denominator and then
okay.
Use 3 for that one
E-
as well, as long as you get rid of the denominators, I guess.
yeah, that's what I did. I found a common denominator. But I don't know if that's even legal.
Well, let's see here.
Like, you could use the 3 anyway, even without using the
Multiply by 14,
Yeah,
you got 35
that's what I did.
x to the 5th plus 7 times 9, which is 63, x to the 4th. What did I say to multiply by? 14 times 15.
15
Two-
and 25. 210, right?
210. I'll take your guys' word for it. My brain, 6 plus, I can do this one, 6 squared. 6 times 14 is 60, 84?
Yeah. So then.
Yeah, so I mean, like, if you're going to use Eisenstein, this is very limiting. It says your only hope is 3,
But it works.
but it works, yeah. I mean, because this is a friendly book problem.
Yeah.
So yeah, so we set
Okay,
again.
So you can't do that. That's what I ended up doing.
Well, why can you do that?
Yep, that's a great question.
So that says that this is irreducible, right?
Yeah.
But look at that. So f of x, the given f of x, right? It's just equal to, what do we say, 14? Times this thing, g of x, right?
Yeah.
So suppose, there's a contradiction, that f of x was reducible. Suppose there was an f1 of x, f2 of x, such that it reduced, right? Well, that would be equal to 14 g of x, right? And so divide 14 the other side. What do we have? We have a reduction of g of x, right?
Oh.
but g of x is irreducible. Yeah.
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 Okay.
Yeah.
Can we do something degrees?
Such as?
Such as, I don't know.
Suppose that f of x and zpx is irreducible. I need to erase something. Number 12? I mean, I can look at it. We'll see. You have f of x polynomial with coefficients in z mod p. P prime, I assume. And he wants us to suppose that f of x is irreducible. Right? P prime. What else? If the degree of f of x is equal to what? Is equal to n. Then prove that zp of x mod the principal ideal generated by f of x is a field with p to the n elements. So we have proved many things, haven't we? Many toys to play with at this point. This is a chapter 17 question. So in the spirit of chapter 17, what should I say about this? Theorem 17.5, which we proved. P of x is irreducible if and only if the ideal generated by P of x is maximal. So here's the logic. Irreducible, f of x rather, implies that the ideal generated by f of x is maximal, right? In the ring ZPX, right? Which then implies that ZPX mod this maximal ideal, right? What do we prove? If you have a ring, well, if you have a commutative ring, I forget the preconditions at the moment actually, but if you have this ring at least, mod that maximal ideal, we have a field.
Right.
So this is isomorphic to this is a field. By that, I mean, so there's two theorems really, that irreducible implies maximal, and then that, mod a maximal ideal is a field. I think this is also a corollary. Yeah, like right, corollary 1, bottom page 301. Okay, so it's a field. Irreducibility gives us that the quotient's a field. The real question then is why are there p to the n elements, right?
Right.
So the degree f of x is equal to that. I think that's just kind of a gory calculation. F of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus plus a1x plus a naught, right? Since the degree of f of x is equal to n, well, we know that a sub n is not equal to 0 as well, right? I mean, so if you think about elements of this factor, you think about this set right here, right? What's that look like? So a typical element is what? It's something like, let's see here, how can I do it? G of x plus the ideal generated by f of x is a typical element of this field. Let me choose a notation that doesn't make me go nuts. So let g of x equal to the summation j equals 0 to infinity. And of course, there's only finitely many things non-zero here, but this is a convenient notation.
Okay.
B sub j, x to the j, right? We have that, oh, and's not equal to 0. So, by the way, this implies what? This also implies that, sorry, see here, x to the n, right, plus the ideal generated by f of x is equal to, let's see here how to say this, minus a n minus 1 over a naught x to the n minus 1 plus, well, I guess minus minus a1 over an and x minus a naught over an plus the ideal. So I have this equality because f of x is in the ideal generated by f of x. So the difference of those elements is f, right? If I look at this guy and then I look at that guy, if you take the difference of those two things, it's exactly, that's not quite right. Sorry, give me a second here. I just want the x to the n there. I mean, this is intuitively speaking, guys, this is 0, you know? So I want to solve for xn, basically.
Oh, because the 3 is n.
Yeah.
Okay.
So I know I can divide by,
Right.
that's supposed to be an. Yeah, sorry. So if I take, let me call this thing Pac-Man, and call this thing Ghost, just for the sake of discussion.
Okay.
If we look at Pac-Man minus the Ghost, and we multiply that by an, we get f of x,
Okay.
which is an element, of course, of the ideal generated by f of x, which goes to show you that that equality is legit. Those are representing the same coset.
Okay.
That means that I can rewrite this as, how to say this? I don't know, I'm trying to think of a decent, like, I lack notational inspiration at the moment. The point is, anything that's larger than x to the n there, and g, I mean, so like basically, I'm struggling to find the right notation at the moment. So we can take, you know, let's say b naught plus b1x plus da 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 plus bn x to the n plus, you know, bn plus 1 x to the n plus 1 plus da 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 plus, well, plus da 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 da, all right, plus, you know, da 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 f of x. Let's see, I can rewrite that as, oh yeah, I remember. So b naught plus b1x plus da 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 plus bn x to the n, right? Plus x to the n times the sum, all right, j equals n plus 1 to infinity of b sub j x to the what? I factored out an x to the n, all right? And I'm starting at n plus 1. So like, that should start at j, I want to say minus n. Yeah, j minus n. So you can check that that works. Okay. But then, and of course, plus the stupid coset. All right. So then that is equal to this b naught plus da 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 plus bn x to the n, right?
Okay.
And then this x to the n, what? Well, that I can replace with what? You know, plus, well, I've got to give it a name, ghost. Times, you know, bn plus 1 x plus bn plus 2 x squared plus da 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 plus f of x, right? So what happens there? So the ghost, right, is only up to the power.
Oh, we didn't fix the. All right.
Oh man, that's still not. Dagnabbit. See, I've still got stuff that's like. See, x squared times ghost still gives me an x to the n plus 1. Curses. I have not found a notation to be convincing yet, but what you do is you just take everything above x to the power n, and you can reduce it to powers less than to this, you know.
Okay.
And
So then you have none of the others.
right, so you can always take anything larger than x to the power n and just keep reducing it down until it's stuff up to power n. I haven't been convincing yet about this. I'm sorry. Anyway, eventually you'll see that an arbitrary nth order polynomial is an arbitrary representative of the field,
Okay.
and then it's just counting because you got
Right.
an that. That seems like n plus 1 though. Oh, right. In fact, not. I should. This doesn't. I don't get to keep that. It's. If you sort through this more carefully, you'll realize that the nth one is not unique. I mean, that one's reduced. The ones that
Right,
you have
reduced to the zero.
all the way up to n minus 1 are the ones you have freedom.
Right.
You can't reduce basically. Well, that's not the right thing to say either. But essentially, 0 to n minus 1 gives you n arbitrary coefficients for representatives, and that's why you have p to the n elements. This is actually a really good problem, and it's kind of the uber version of the previous view in this book. I mean, so you know, you're asked to construct a field with what, 27 elements?
Yeah.
So basically, you just want, I mean, I guess I would use,
I use C3
yeah,
and
you want something that's
I use
fourth order, right? Well, let's see here, p to the n.
I think I used order 3.
I guess you need a cubic, right?
Yeah.
Yeah.
Yeah, I used the cubic.
You need an irreducible cubic, so how about x cubed plus 2x squared plus
Plus
2?
That's what I use.
Oh, really? Oh, that's whack. That's funny. So I just let Eisenstein be your guide,
Okay.
right?
Yeah.
That's funny. That's funny. No, I literally just guessed that. I mean, so yeah.
Okay.
So I hope I've communicated to you the idea of number 12. I just have not yet imparted to you have to make the right notational choice here to communicate the reduction properly. I haven't done that yet. Sorry about that.
That's okay.
Oh, yeah, I best be, oh, you're fine. I'm the one that cannibalized your help session and give extra magic hour lecture today. Let's see here. La la la. Oh man,
What?
I had the. Oh, you just don't.
Was it?
It was up.
No.
Oh man. Sorry guys. Oh well. At least you get to see it now, right? Although, I mean, in some sense, the words I said are more important than the. Well, I wrote something. Listen to me. I think I drew high on the board. Well, anyway, it's what's done is done.
Most of it was high enough that it could go to somewhere.